In this chapter, we are going to talk about combinational logic circuits. First, let's know what are combinational logic circuits. In a sequential logic circuit, outputs are depend on both their present inputs and their previous output state, which gives them some form of memory. But in combinational logic circuits, the outputs are only determined by the logical function of their current input state, logic 0 or logic 1, at any given instant in time. The result is that combinational logic circuits have no feedback, and any changes to their signals being applied to their inputs will immediately have an effect on the output. In other words, in a combinational logic circuit, the output is dependent at all times on the combination of its input. Thus, the combinational logic circuit is memoryless, and there are no feedback loops in combinational logic circuits. Let's see how these combinational logics are made. We can use the basic three logic gates, which are AND, OR and NOT, to make this logic combinational logic. And also we can use the gates that derived from these basic three gates, NAND, NOR, XOR and XNOR. These gates are combined or connected and they make complicated switching circuits. This is how a combinational logics are made. There are three main ways to specify the function of a combinational logic circuit. The first way is Boolean algebra. This forms an algebraic expression showing the operation of the logic circuit for each input variable, either true or false. And the second way is the truth table. A truth table defines the function of a logic gate by providing concise list that shows all the output states in a tabular form for each possible combination of input variables that the gate could encounter. And the third way is logic diagram. This is graphical representation of a logic circuit that shows the wiring and connection of each individual logic gate represented by specific graphical symbol that implements the logic circuits. Let's talk about the uses of this combinational logic circuit. There are many uses, but here I mention some of them, which are adder, subtractor, converter, encoder, decoder, multiplexers and demultiplexers. Now we are going to build a sample combinational logic circuit using an expression. So, this is the expression that we use to build our combinational circuit. The expression is Q is equal to the bar of A and B and the bar of A or B and C. So we can make the truth table for this expression like this, and we can then build the circuit. So this is the illustration of the logic gate circuit, and let's see how we can implement this circuit in our logic simulator. Let's move to that. Now we are going to build the logic circuit for this equation. So the equation is the whole inversion of A and B and the whole inversion of A or B and C. So we can identify that there are three inputs which are A, B and C. So let's get three inputs and name them. So this is, we can name this input as A, so this is A, and input for B we can copy this name and paste it here, and we can rename it as B. So there is another input. So we can paste the name that we copied earlier and rename it as C. So we can see the connection between A and B in the first part. It is a NAND gate. We can see the inversion of A and B. So let's get a NAND gate, 2-input NAND gate, and place it here, and we can connect A and B to this NAND gate. And we can see the next connection between A and B is a NOR gate, which is the whole inversion of A or B. So we can get a NOR gate, a 2-input NOR gate, and we can place it here and connect A and B. First we connect A. Then we can connect B. Like this. I drag this NOR gate to a little bit down so the circuit will be more clear, and I will drag this input to a little bit down, and this is it. And the final gate, it is a NAND gate. We can say there is an AND operation in here and operation in here. The AND operation of all three parts. So as for this AND gate, it has 3 inputs. We have to get a 3-input AND gate, and we can place it here, and we can connect the inputs for this AND gate. The first input is the whole inversion of A and B, and the second input is the whole inversion of A or B, and the last input is C. So the output is connected to this AND gate, so we can connect it. We can name it as Q. So this is the circuit for our expression, and let's get the truth table for this circuit and check this circuit. So this is the truth table for this circuit, and let's check each of these cases. In the first one, all A, B, C are 0 and Q is 0. We can see that in here all A, B and C are 0, the Q is 0. In the second, only the C is 1, then the output must be 1. Let's check it. The C is 1, we can see the output is 1. And in the third row, A is 0, B is 1 and C is 0. Then the output must be 0. So only the B is 1. We can see the output is 0. In the fourth one, B and C are 1 and A is 0. In here also the output must be 0. The B and C are 1. We can say the output is 0. And in the next one, only A is 1. So we can say the output is 0. In next one, only A and C are 1 and B is 0. A and C are 1, B is 0, the output is 0. Next one, A and B are 0, A and B are 1, C is 0, so the output must be 0. A and B are 0, as expected, the output is 0. In the last one, all the three input A, B and C are 1, then the output must be 1. Let's check it. All A, B and C are 1, so as expected, the output is 0. So this circuit is compatible with this truth table. So this is how we can build a combinational logic circuit using our logic simulator.